me welcome the next speaker. This is Sabrine Chebbi from here, from AIM South Africa, and she will speak about the interaction between PDEs and machine learning.
Okay, hello everyone. So yeah, today I will be speaking about the interaction between PDEs and machine learning. But let me motivate the title by saying that I had my PhD at University of Tunis Al-Manar, and I was mainly focused on the study of partial differential equation. More precisely, I was focused on the long-time behavior of the solution. So I had the opportunity to come here at AIM South Africa and also to be visiting research at the University of Tübingen. So I was surrounded by people who are interested in machine learning and AI and stuff like this. And 1 year ago, it was all completely new for me. So I was wondering, how can I see the interaction between partial differential equation and machine learning? And this is what motivates my talk today. So in the sense of on the sense of finding this bridge between machine learning and partial differential equation. So going from machine learning to partial differential equation, I was trying to investigate robustness between machine learning tools such that physics-informed neural network and other machine learning tools to solve partial differential equation. And also in the other sense that in the other way, like taking the framework of partial differential equation or the partial differential approach, how could be perform a theoretical setting of reinforcement learning, or more precisely on the context of multi-armed bandit problem. And so today my presentation, it will be mainly focused on this physics-informed neural network for solving partial differential equation. Yeah. Also, as a motivation, so we all heard about AI in this event, and we know that this is it has achieved a remarkable success in both academia and industry. So a branch of AI, we have machine learning, and more precisely, so machine learning is about having an algorithm which is able to predict a solution, either based on interaction with the environment or based on a given data. So more precisely, we have physics-informed machine learning. And when I say physics-informed machine learning, is about including the information coming from the physics itself to predict the solution. So how can we use this progressing technology in order to solve partial differential equation? Okay, so the first question that came to my mind, to our mind, what is physics-informed neural network? And the first part in physics-informed neural network is an artificial neural network. And in deep learning, we have two big categories of structure of neural network. We have the fully connected neural network, and we have the convolutional neural network. And for this tool, we will be using a fully connected neural network. I mean that all the layers are connected to each other. Okay. How can I? Okay. Like this? Okay. I'm not good in technology. Okay. Okay, and then, okay. I destroyed everything. Okay, so it's okay. So, okay, fully connected neural network, that I mean all the layers are connected to each other. So as you can see, the structure of a neural network is defined by compositional function. That means we are taking the x, which represent the input, and then we multiply it by a weight function, weight vector, and then it adds some basis. So it's a linear transformation, and then we apply a non-activation function, which is denoted here by sigma. So the input of the output of the first layer will play the role of the input of the second layer, and so on and so far. We will repeat this process L number of layers. And the optimization problem is given by minimizing a loss function, which is some function that depend of the neural network. Okay, so the question is how can we use or apply this architecture in order to address the partial differential equation? And to do that, we have two approaches, either the supervised approaches, either the unsupervised approaches. When I say supervised approaches, that means we are trying to use another solver. That solver could be any analytical solution, like we calculate the solution, or we can use any other numerical method, such that finite element method or finite differential method, in order to generate a data set of solution. And once we have this data set of solution, we just need to train the neural network in order to learn the mapping from X to UX. And then the hope is once we have a new input, so we are able to predict the solution that in such a way we have a minimum between the loss between neural network and the solution obtained. So in this approach, we need another solver, but it's not an easy task. Not necessarily we have an exact solution, and not necessarily like traditional numerical method can be exponential or very expensive computational. So the unsupervised approach, while in the unsupervised approach, all what we need is to select a random collocation point, and then solve the partial differential equation by minimizing one single loss function, which include all the constraints of the problem. And as you can see here, we have this minimizing a loss function between the neural network, and also I will add a quantity that I call physics loss, thanks to the PDE residual. And I will explain this part later. So the hope is once we train the neural network, we will approximate the partial differential equation. And as you can see in this approach, we will not need any knowledge about the actual solution. So PINS is about, in few words, is an unsupervised approach that uses the information coming from the PDE to predict its solution. Okay, so this is the definition of PINS. So we would like to apply this machine learning tool to solve a system which is, okay, let me tell you the story of this system, because there is a phenomena that has been happened in 1940, in which we have this famous Tacoma Bridge that has been open to traffic on 1st of July 1940, but suddenly it has been collapsed on the same year. So this phenomena has attracted the attention of mathematicians, engineering, and physicists in the sense of understanding the deformation or the oscillation of a beam structure. And physically, so we have two theories that has been, or two models that has been established in order to understand the deformation of a beam structure. And here we have the Timoshenko system, the Timoshenko theory, and the Euler-Bernoulli theory. So the Timoshenko theory is considered to be more general because it takes into account the shear deformation, and also it takes into account a rotation angle. And so mathematically speaking, and I'm really interested to this part, so we will be having a system which is composed by 4 partial differential equations. In such a way, we have 4 unknowns, which are phi represent the displacement vector, psi represent the rotation angle, theta represent the temperature and the heat flow. So the classical system was only composed by the first 2 partial differential equations, and we wanted to have a more general system. That's why we added more features such that the temperature and the heat flow. And the fact of saying that it's a couplet, because as you can see, all the partial differential equations are related together. So yeah, so we would like to use the PINS in order to solve such a system. And the first question that came to our mind as a mathematician is either this system is well-Posness or not. So in order to prove the existence and uniqueness of the solution, we need to add a boundary condition, which are here mixed directly in Newman boundary condition, and also initial condition to ensure the uniqueness of the solution. So yeah, and we have this result of existence and uniqueness of the solution that has been established in my previous work. Okay, so we will, in this figure, you will see that we are adapting the PINS framework to the Timoshenko system. So here we have, okay, so here we have the input that are, which are X and T, because we have a variable space and a time variable. And we have the activation function, which is sigma. And you can see in the first part that I represent only one hiding layer, but this is not necessarily the case, because I will later precise how many layers I put in order to predict the solution. And then as an output, we have 4 unknowns, which are the phi, psi, theta, and q. So once we have this output, we need to include the information coming from the PDEs itself. And we use the automatic differentiation in order to be sure that the neural network will satisfy also the partial differential equation. And the goal is to minimize the total loss. And once we have a minimum value of a total loss, so we are done. Otherwise, we need to come back again and proceed and repeat the process in order to find a minimum total loss. And while we are coming back, we need to change either, I don't know, either the activation function, either the number of hiding layer, so in order to obtain the minimum total loss. And this part of discrete energy, I will explain it later. So once we have this framework, we are able to predict a solution. But mathematically speaking, so we need first of all to select a number of collocation points in interior and on the domain. And we need to approximate the solution by a neural network. That means we are taking an approximation of the solution denoted by phi, x, t, and also depend of the parameter of the neural network. And then we define the residual of the system, in the sense that the neural network will satisfy the PDE and also the residual for the boundary condition and for the initial condition. And you can remark that once we have all the residual are equal to 0, so we have the exact solution of the system. In order to define the loss function, we need to define the mean square root error to every residual. That means we are taking 1 over n, the number of collocation points of each residual. Okay, so in order to test the performance of PINs, we need first of all, as I said, so for the Timoshenko system, we don't know any exact solution. So we wanted to compare the performance of PINs with a constructed or by building a new an exact solution. And what I mean by that is we are taking all the parameter, so in the system, rho 1, rho 2, rho 3, theta, etc. are corresponding to a physical parameter, which are in our case supposed to be a positive constant. So we are taking them all equal to 1, and we are assuming that we have an exact solution of the form for exponential t x 1 minus x. And the only reason why we are taking this exact solution of this form is that satisfy the Dirichlet homogeneous boundary condition. So once we inject this exact solution in the system, we will obtain a new system. In such a way, he already has an exact solution, but we can see there is there is a source term, while in the Timoshenko system, in the old Timoshenko system, we only have 0 as a source term. So for this, we train the neural network, the PINs tools by setup. So we have here a fully connected neural network by using PyTorch. So as I said, the input are 2 neurons corresponding to time and space, and we will take 5 hiding layers. And the output are 4 neurons, and the activation function is a parabolic tangent, and we are taking the Adam optimizer, and we are training the data set for 3,000 randomly selected collocation points. And we are training the neural network for 10,000 epochs. And that's what we'll find. So in this figure, you can see the total loss and also the PDE loss. So we can see that the loss is taking a minimum value, and very near to 0, and also for the PDE loss. And in this figure, we plotted the exact solution that we already built it for S exact, and we compare it with the PIN solution. And we can see that the error is really slow by plotting the relative error, which is defined as follows. So once we already tested the PIN's performance, we will be able to solve our initial system, in which we don't have the exact solution, and also we don't have the source term. So in order to do that, we first of all test the solution of the Timoshenko system based on this stability number. And this stability number has a theoretical story, because all the people who were interested in Timoshenko system or the stability of Timoshenko system, they are trying to study the decay rate of the energy based on this stability number. So what I wanted to do is just to take the boundary condition, the Dirichlet homogeneous boundary condition, and take for Xi equals 0 and Xi different than 0. And, sorry. We obtained the behavior of the solution. So once at the beginning we did not know any information about the solution of the system, but here we are able to see the behavior of each unknown of the system, like every unknown phi, psi, theta, and q. For both cases, for Xi equals 0 and Xi different than 0. Okay, and to be sure, to convince the machine learning people, so we need to plot the total loss and also all the training loss for PDE and initial condition and boundary condition. And you can see that the loss is going to a minimum value which near to 0. Okay, you remember I told you that I will let the part for discrete energy for later. So once we have the existence and uniqueness of the solution associated to the Timoshenko system, we are able to define a quantity called energy, which is associated to the solution. So in order to see the stability of the system, we need to see the long time behavior of this energy function. And mathematically speaking, if you would like to determine the derivation of this energy, we need to multiply formally the first equation and the second equation and the third equation in this, in this system by phi t, psi t, theta, and q, and we will find that the first derivative with respect to time of the energy is equal to a negative quantity that confirms that the energy is a decreasing function. And in order to include this information also in the algorithm that we already use it to solve the Timoshenko system, we need to approximate the energy by this quantity. And at this level, we can use the finite difference method in order to approximate this functional, which depend of phi, psi, and theta, and q. So once we approximate the energy, we are taking, as you can see here, phi tilde, which represent the neural network. So as a result of, so we are taking the predicted solution and we are trying to see either this energy will, either the obtained solution will give me an characterization of the approximated energy. And that's what we found. We found results which are in coherence with the theoretical result, in the sense that we know that the energy is a decreasing function, and we know that when time goes to infinity, the energy will be decaying to equilibrium state, and that's what we call it strong stability of the energy. And later on, we wanted also to identify or characterize the decay rate of the energy, in the sense either to see this energy, this function will be decaying as an exponential function or as a polynomial function. And when I say exponential function, that means the energy is less or equal than a constant, exponential minus this constant t. So as you can see here, we plotted the energy as a function of time, and also we plotted ln of the energy as a function of time. And we can see we have the exponential decay rate of the energy. Okay, so there are other cases also we treated by using pins, but I wanted, if you remember at the first of this talk, I told you that I'm trying to find this bridge going from machine learning to partial differential equation and also coming back. So yeah, I hope that it will not be a Takuma bridge, because I want stronger bridge that take me from PDEs to machine learning. And here the goal is to try to use the partial differential equation, and I only have 5 minutes, okay? So I need to use the partial differential approach, PDE approach, in order to study the continuous time limit of multi-armed bandit problem. And I will, because this was also the subject of my poster yesterday, so multi-armed bandit problem, for the people who don't know it, it's a one-state reinforcement learning. And the example that came to my mind, it could be like you have two model of a website, and you would like the people choose between both of them. So you publish the website for, I don't know, for 1 month, and people will click on it, and then you switch and you compare those clicks on the website. So this is like A/B test, or also multi-armed bandit problem can be used for medical treatment. And other, like Netflix, Amazon, all those application, real-world application. Okay, so bandit's setting is about having a learner or an agent which is faced on multiple decisions, and he's trying to select one of them. And at each round, so the environment would choose a vector of reward, and the learner choose an arm, which by pulling this arm, you will receive a reward. And the main goal of this problem is to balance between exploration and exploitation. And the fact of saying exploration, that means the reward of the arm that are not sampled are not relieved to the learner. So it's an incomplete information. So the learner will need to repeat the process over and over in order to gain more information. Okay, and exploitation is about if you pull the bad arm, you will suffer of regret. So you need to reduce the regret and by repeatedly pulling the best arm that you don't know it at the beginning. So as I said, you need to balance between exploration and exploitation, and how you do that by following an optimal policy. So my goal was to try to use the approach, the PDE approach, in order to obtain or approximate an optimal strategy for this. Okay, so this setting is a stochastic because we have randomness either coming from pulling the arms, either coming from the reward itself because it's a random variable. So the goal is either maximizing the expected reward, either minimizing the regret. And in some cases, it will be better to minimize the regret better than maximizing the reward. So this regret is once you finish the game, you already know the best arm. So imagine if you were supposed to pull this best arm at the beginning. So at round 1, you had an expected or a mean, which is mu k star. So you are trying, you suppose that you are pulling this arm all the rounds. So you have n mu k star and minus the cumulative reward that you get it by playing. Okay, so for this setting, we have 2 minutes. Okay, we have 2 measures of performance. We have the Bayesian setting and the frequentist setting. So the Bayesian setting, if you assume that you have an additional information, so you have a prior, and it's defined by the expectation of something. While for the frequentist setting, it's about having a worst case regret. So my idea was to find an interpretation between those 2 settings. So once you know information about the Bayesian setting, you can deduce something about the frequentist setting. And a relation between both of them is represented by what I called lambda exponential Bayesian regret. And I borrow this expression from the financial area, in which they took for lambda equal to 0, so this quantity will goes to expectation, but while when lambda goes to infinity, it's exactly the worst case regret. So what we wanted to do is to test the continuous time limit. That means I will need to do rescaling, and we're not be speaking on the context of a discrete context, while I will take all of this to a continuous context, and I will find this partial differential equation that explain the variation of the risk of performance while time is continuous. And going back to background, my background in PDEs, I remarked that this partial differential equation need to be satisfies the well-posedness. So with the presence of this blue term, which is a quadratic term, so it will be a little bit difficult. So I used the trick of exponential transformed equation by changing a variable, like variable change by assuming this phi is equal to exponential lambda something. I obtained this equation without the quadratic term. And once we have this equation, we can deduce that the limit of the optimal policy is given as follow. Okay, I think this part needs more details. And if you have a question, I will be welcome to explain it. And those are, I will end by thanking my collaborator from AIM South Africa, Boubacar and Joseph, and also from Tübingen University, Setera and Sofiane. Thank you so much for your attention.
Thank you very much, Sabrine. So, questions?
Thank you for your nice presentation. I very enjoyed this presentation. So I was asking about, I want to ask about the solution of the neural network and the information provided by the PDE itself. Is that numbers or is that function? And how do you do to manage, to compute the distance between the information provided by the neural network and the PDE itself?
Okay, I see. Thank you so much for your question. So the fact that we are taking an information from the PDEs and using it for this machine learning tool is the fact that, first of all, you will, if you know the traditional numerical method, so you have the partial differential equation and you try to discretize. So you are approximating the derivation with respect to time, to x, etc., by another quantity. In this case, you are taking the neural network, which is the output, and you have something called the automatic differentiation. So you will not need to approximate once again the derivation. You are directly taking the neural network and injected directly in the PDEs. That's what I defined by residual and the mean square root error. So the information is exactly from the residual that is the neural network applied to the partial differential equation. Is it clear? Or? Okay.
Maybe one more question, if there is.
Yeah.
Okay. Thank you for this nice presentation. I just have maybe two questions. The first one, what is the cost effectiveness of doing this using physical neural networks to solve your PDs instead of using those classical methods we used to do?
Okay.
What is the
can
advantage?
Can I answer this one?
Yeah.
Okay, as I said, so for the traditional numerical method, it's, for example, if you are in high dimension, it will be very taking time and very exponential cost. So we are trying, once you train the neural network, it's easier and you have this general framework. So you just need to change some parameter and you can use the same algorithm. So this is what it facilitates the thing. And also for hyperbolic equation, in the traditional numerical method, you need to balance, you have this condition which link the time step and the space step, which is CFL condition. While for pins, you can see I did not take anything. I just took a random collocation point, which is following a uniform distribution. So I don't have this link between, or condition between the time step and step.
Okay, and the other question is, how can we apply this? Do you have an idea of any application in partial integral differential equations?
In?
Partial integral differential equations. When you have an integral in your...
Yeah, you have integral. Okay, I think you need, I didn't do that, but I think you need to approximate the integral before using the pins. Or maybe you take, I don't know, you take the neural network and you assume that the residual will be including the integral. No, I think you need to approximate the integral before.
Thank you.
Okay, maybe let's take further questions offline. In the meantime, thank you so much again, Sabrine.
Thank you so much.